Good evening, Dr. Low. This is Navneet Verma. My research paper title is An Efficient Algorithm for Multiple Traveling Salesman Problem. The problem statement for multiple traveling salesman problem reads as follows. Given a set of cities, which is indicated by these nodes, and an office or a depot, the problem is to come up with the minimum cost tour for M salesmen. In this figure, you see there are 3 salesmen, and we have to arrive at the optimal traversal order as well as the proper city assignment for each salesman. So for example, you can see here is that salesman 1 has been assigned these blue nodes as the set of the cities among all the cities, and similarly salesman 2 has been assigned these green nodes, and salesman 3 has been assigned these red nodes. So there are 2 problems that need to be solved. First is the assignment of the cities to the salesman, and then coming up with the correct traversal order. So that's why this problem is more difficult than TSP, which is an NP hard problem. And by NP hard, we mean that all the problems in set NP can be reduced to this problem. The decision problem is NP complete. But the optimization problem is an NP hard problem. And we shall see that the multiple traveling salesman problem can be reduced to traveling salesman problem with some reduction technique applied that we learned in the course. So this is the problem statement. And now we move to the next topic, which is the methodology that we use to solve this problem. So primarily, the methodology used was to use mixed integer programming to solve this particular problem. And mixed integer programming is very similar to Prolog declarative style programming, in which you have an objective or a goal, which is specified by this objective function here. You can see is that Cij is the cost of travel between city I and j, and Xij is a binary variable. So Cij multiplied with binary variable Xij is the expression which is summed over for all I and all j, which basically there are n cities in the problem. So there is some summation, double summation over all the I and j's. And Cij is the cost of travel, as I said, between I and j, and Xij is 1 if route from I to j is taken. I mean, it need not be taken, but so that's why there's a flexibility. And the MIP solver is going to come up with the solution to this particular problem, like which values of Xij should be 1 and which should be 0. And so this is an objective function. And then there are a bunch of constraints that we put in. Like constraints are, again, declarative style constraints, which state that each city must be exited once and entered only once. So, these are exit and entry constraints, as you can see. And the way to understand these constraints is that, like, for all I, like, so for a given I, like we just try to sum up all the j's, and it should exit, like if you enter at one given I, it should exit at some j. And similarly, if you given a j, then you must enter at some I. So these are the 2 constraints that we have. Now, one key thing about this formulation is that although this formulation looks correct, because that's what a tour is about, this formulation will result in subtours. And by subtours, what do we really mean? So this is illustrated here. So we have a cities, like 8 cities, and in the 8 cities, like you can form a subgroup, like you can go from 1 to 4 to 3 and back to 1. And like, again, you can also have 2 to 9 to 6, 7, 5, 8, and back to 2. So again, I mean, I think there are 9 cities actually. So So that's the idea, that the subtours can be formed, and these are not desirable, and uh, some some logic needs to be applied so that the subtours are not there in the solution. So one of the key points of methodology was that we use this iterative subtour elimination technique. And what that does is that once a MEP solver produces a solution, then the solution is refined. If we do find these subtours, then we refine them by making sure that there is an arc flowing from here to here, and then arc flowing back from this group to that group. So that way, the subtours are eliminated, and that's an effective way to to eliminate subtours rather than enumerating all the subtours, which could be very, very hard, because there could be lots and lots of subtour and exponential number of subtours. So we use this lazy approach in which we eliminate the subtours only when we detect them. If the solver says that finds a solution which has a subtours, then we detect and eliminate iteratively. And as we will see, that this technique works pretty good. So the other part that is part of the methodology is called k-means clustering. So what k-means clustering does is it groups the cities and it solves the assignment problem. So if you go back here, I mean, like, we are given all these cities, and like, how do we assign like the blue dots to salesman 1 and green dots to salesman 2 and red dots to salesman 3? That has to be done, and we do it by using k-means clustering, some very innovative way of a variant of k-means clustering, which uses the angles. So basically, like the cities which are closest, like suppose this is the origin, so the cities which subtend the angles which are closer to each other, they are grouped into one group and another. So as you can see that all the green cities have like very closely matching angles, or angles different, like from this blue dots and red dots, like they're. So that's why all these guys will be grouped into one, and another one will be grouped into two, and another group will be grouped into three. The three groups will form. And obviously, there were some challenges in k-means clustering that are detailed in the paper. And one of the challenges was that k-means clustering is very sensitive to the start of the median as the centroids. So we did some ways to resolve that and make it more predictable by making sure we repeat k-means clustering over and over again. So just kind of like make sure that we have even division of all the cities. Then we leave the MEP solver to do the traversal problem. So this kind of division of labor works pretty good, because if we are asking the MEP solver to do the both, that basically do the assignment of the cities as well as do the traversal order, it can MEP solver can be loaded a lot, and obviously that's some pre-work that we do in k-means clustering, and then we turn the MEP solver loose. That we found was more efficient. So this is the methodology we used, and why we chose this methodology. I think we have done some literature survey to illustrate the point in my paper, is that a lot of research was in genetic algorithms. So where there's a mostly probabilistic algorithm which used the Darwin's theory of natural selection, evolution of a solution, and some of these algorithms are ant colony optimization, and then simulated annealing, and various other techniques such as genetic algorithms. Like all these techniques form a group of genetic algorithms. And I'm sorry, the probabilistic technique, sorry, not genetic algorithms, is one of the other techniques. So the issue there that I highlighted in the paper is that there is a premature termination, or like a premature convergence, which is a big issue. And like determining the exact parameters for these genetic algorithms isn't quite easy, because I mean, like, what should be the degree of mutation? What should be the degree of crossover? I mean, those are not easy things to guess, and there's a lot of trial and error involved. While this technique doesn't have any trial and error involved, and there's a neat division of labor and integer programming. It's a very solid technique to solve these problems. So this is the reason why we chose this methodology. Now we share some results. What we did was, first of all, I mean, like, how do we know that this, all this stuff that we have stated here in terms of subtotal elimination, this was all correct? So we matched the results with the published website, and just for one traveling salesman, we matched the results, and we found that, okay, our objective function value was exactly equal to the one published on the website. So that proves that this particular technique is correct. And the second thing that we did was, then we tried to, after ascertaining that this technique was correct, the correctness of the algorithm, then we said, okay, you know what? Why don't we try to solve this problem with two salesmen for a 48 city data set? And as you can see here, I mean, the way to read this graph is like these are the cities, like there are 48 of them in the number, and this is the ordinal position. So that's how we need to read this graph. So what this basically means is that like a city, for example, this given city will have, like, let's say this city 30 has an ordinal position 10 in the tour. So basically what it basically means is that city figures 10th in the 10th position for the tour. Now, before we also try to talk about this graph, we also need to talk about a reduction technique that we learned in the class, and so that we can understand this graph. So let me just go back to the paper and just end the shoot just a second, and go back to the paper to illustrate the point of what that technique was that we studied in the class. So it's right here. Okay, so what the reduction technique? So okay, first of all, let's talk about the reduction of one language to another that we learned in the class, the L1 to L2. So if X is in L1, if and only if fx is in L2, that's the reduction. So basically, it's equivalent to solve if one problem. You can solve L2, the L2 is equivalent to L1. Like, so if you can solve problem P2, then it's equivalent to solving problem P1. So how we reduce the multiple traveling salesman problem to traveling salesman problem. And again, I mean, this is coming again from a paper that I read. So what happens is that, suppose like these are the tours, like that's the first we discussed, like these are the tours for the two salesmen. Then we add a like extra city which has the same coordinate as the depot or the origin, and that is added to the mix and bring added feed of the MIP solver, and that really worked very well. So our conclusion is that the integrated approach combining the k-means clustering with mixed lineage programming problem with reduction is an effective way to solve MTSP problem, like so around 50 cities. Like just to say with the caveat, because we haven't really tested with more cities, but that's the main conclusion here. And if enough computing power is available, each of the groups of the cities, we can solve it in parallel. So we can use the parallelization to achieve desired scalability for larger data sets. And one final comment I have is that some of the modifications can be made to the clustering algorithm and to solve this problem for capacitative vehicle routing problem. So which basically means distribution of LNG to different places, and various other problems, repairment, scheduling, all these optimization problems can be solved. So essentially, more research is needed to apply this technique to VRP, like which is vehicle routing problem, and make it useful for a larger data sets. And more experiments need to be done for the larger data sets. Enjoyed really working on this course, and of course, I want to thank you, Dr. Lowe, for the wonderful class. Learned a lot, especially about the problem reduction that learned in the class. I was able to apply here, and really appreciate all the knowledge and all the help you have provided. And thank you so much for being always available to us and being so gracious. Thank you. Bye-bye.